Okay. Mass continuity. What are you gonna say? Mass continuity. Okay, so what we are looking at here is the idea of mass continuity. And you have probably dealt with mass continuity in your life without actually realizing it. What we are essentially saying with mass continuity is that because fluids are incompressible, the same amount of fluid has to go through each side of an opening if you've got two openings there. And what I mean is this. If we have a small opening, or here, we'll do it this way. If we've got a large opening, and then this collapses down and becomes a small opening, like this, here's area 1, here's area 2. If the speed of the fluid going through here is V1, the amount of volume of this fluid that is moving forward each moment in time, that volume has to be coming out of the other end. And since that has a different area, we know that this might have to move differently. You've probably done this before. If you have a garden hose at home and you turn on your spigot, the water just starts going out, right? It's in a nice little cylinder, it droops onto the ground. But if your friend's 15 feet away and it's the middle of summer and you're having a water gun fight and you've got the holy hose, there's one solution to win the war. You take your thumb, you put it over the hole, and then now that water's jetting out there. They're like, stop, stop. You're like, no mercy. And that's that. You've won the water fight. Congratulations. You did it. That is what we're employing here. It's just mass continuity. We're going to set this up so that this mass continuity is going to work for fluid flows, and we're going to see how it relates to velocities. Because when you put your thumb over that spigot, the water shoots out farther because it's going faster. So we're going to see how this all relates here. So what we can say is that the change of mass in some region, so delta M, okay, it's just some change in mass, and we'll call it delta M1, in some amount of time, this must be equal to the change in mass, we'll call it M2, in that same amount of time. So whatever mass is coming through here, this mass up here that we had, that amount of mass coming through this has to be equal to the same amount of mass back here. And we initially talked about that as the same amount of volume, because if this is something like water, it has the same density, and we know that for a fluid, the mass can be found just by saying a density multiplied by volume. So when we talk about mass, when we talk about volume in this case, because fluids are incompressible, we're really saying potato, potato. So the masses are the same. Because of this, we will just rewrite this as saying the density at the beginning and the volume at the beginning over some amount of time equals the density, which is the same as the beginning, so we'll just write this as rho 1 again, multiplied by the volume of the second half divided by time. Now, these densities are the same here, so who really cares? But let's rewrite this volume, okay? Because while this volume, we know it could be different, or we know that volume is going to be the same, it's shaped differently. We know a volume is shaped by a cross-sectional area and then some depth or some distance, right? An area is meters squared. If we multiply that with some length or some distance, we get meters cubed. That's a volume. So let's go back down here and rewrite this as saying this volume is a cross-sectional area multiplied by some change in length. This is like the length of the water, how much depth you have in that hose. We'll call that delta L1 divided by some period of time. This is going to equal to the second cross-sectional area, our either thinner or larger opening, multiplied by delta L2 divided by some amount of time. And these delta L1s, these delta L2s we're talking about are, if we go up to our picture, this is a very small delta L1, but this is a very long delta L2, just because that volume needs to be the same. if we've got a thinner cross-sectional area or a less wider one, smaller diameter, we have to have a longer tube in order to get that same amount of volume. If we have a very wide one, we can make it very short. It's going to be the same amount of volume. Okay? Now, a really cool thing we can do at this point is to recognize the following. Delta L over T, that's a change in distance or displacement, so meters, divided by time, seconds. Meters per second? What? Do my ears deceive me? We know what that is. That's a speed. So we could just rewrite this as saying A1 V1 equals A2 V2. And this is our mass continuity equation. This equation right here, even though it doesn't have mass in it at all, for fluids, we saw how we used mass to get here, and it shows us that whatever mass we put into a system, that is the same amount of mass we're getting out of the system. The fluid just had to speed up. This makes sense with your garden hose. You put your thumb over the opening, the water still got to get out, but since you decreased the cross-sectional area, the velocity had to increase because A1 V1 was some constant value. That water's got to flow. Okay? So that's what we're looking at in these mass continuity ideas. The water needs to flow. If you close off a cross-sectional area, your velocity will change. More narrow regions are going to have faster velocity. Larger regions will have a lower or slower velocity. Okay? That just kind of makes sense with what you've experienced in your real life and what we see with the mathematical setup. Okay? So with that, this mass continuity is finished. In our next videos, we'll start seeing how we can start conserving energy using mass continuity and build Big Ol' Bernoulli. But until then, adios and take it easy.